Rocky, this is who goes first. Best out of three. And you win.
Hi, I'm David Bach, and today we're talking about part 2 of our series on computational thinking. As a quick refresher, we've been talking about the 5 concepts of computational thinking. Today we're going to talk about data collection and analysis.
B1.
Miss. J10.
Miss.
Now, you might think that Battleship is a pretty simple game. After all, it seems like you're randomly picking places to fire into an ocean, and that randomness would probably have a lot to do with the outcome of the game. And it does, but there are some worthy strategies to talk about. If you've ever played Battleship, you quickly learn that the minute you hit something, you start targeting around that spot. So that's a much better algorithm than just randomly shooting, right? If you were to just randomly shoot, that game would take forever. The minute you know where something is, it makes sense to target around that area. And that's actually a worthy strategy called hunt and target. And this blog, called Data Genetics, goes into several algorithms. They first analyze games completed with just pure randomness, and they analyze 18 million games for this. And you can see that the number of shots, at first it's very slow. Very rarely does a game ever finish even in 70, 75 shots. It does happen, but by and large, we're talking it takes over 90 shots, 95, just to even get to kind of like a halfway point of the number of games. It's a very inefficient strategy. So of course, hunt target is the much better strategy that we've already identified. Here we can see that the average game is finishing around 64, 65 shots. But there is a much better strategy we can employ, and my children have figured it out, given enough games to play. It's based on the parity of the game. That is, the smallest ship is the tugboat. It's 2 squares in size, so you never have to target half of the squares. You're guaranteed to hit that boat if you target every other square. So you can target basically just the black squares on a checkerboard. So what does hunt target with parity do for us? We can see that gives us a small edge of 4 or 5 moves on average. And amongst kids playing the game, that will pan out on average over 6 million games. But there's an even better strategy. If taking into account the size of the smallest ship makes sense, we can take into account the size of all the ships and build what's called a heat map of probabilities of where ships can be. We know that if we hit a spot 4 spaces away from the edge, the 5 square aircraft carrier cannot fit there. So we know that there's less likelihood of anything being there. There can be ships there, but the largest one can't be. So if we keep applying that statistical likelihood to all squares, we can build a heat map based on our projected location of targets. And as long as we're always targeting the hottest spot of the map, we can get quite an advantage at this game. Now, this is a little hard to calculate in real time, but you can get a feel for it if you follow through the text of this article. And as you see from this graph, it gives us quite the edge. With the hunt and target, even hunt and target with parity, we're finishing games between 62 and 65 shots on average. But if you look at the heat map strategy, we are finishing games around 42, 43 on average. So that's a 20 shot advantage for this strategy. That will definitely pan out. Now, you see that these two graphs do overlap, so luck is going to have some say in this, in that occasionally the other strategy will win out. But by and large, that is a winning strategy. This unnamed algorithm in this paper that I'm calling a statistical heat map. And then give you a walkthrough of how this algorithm works so that you can apply that, learn how it works well enough to instinctively play this way as you play. I'll include a link to this article in the description of the video. This company has also done a mathematical analysis of Chutes and Ladders, and this is based entirely on die roll, but there are some interesting questions that you can ask about this game too, but that's another story. And our other example today is a game called Mastermind that is kind of hard to explain, so I'd rather just show you Mastermind in action. I have a version of it here on my iPad, and we'll just walk through a simple game. Okay, so bear with me as I try to solve a Mastermind puzzle live. I'm going to do a code size of 4, have a maximum of 8 attempts, and I'm going to allow repeat colors. So I'll explain what all that means as we go. The computer has 6 colors to choose from, and it's choosing 4 colors at random with duplicates allowed. So you see the 4 colors at the bottom: red, blue, green, yellow, orange, and purple. Well, the computer selected 4 colors of those, and there can be duplicates allowed, and I need to guess what it is. And on the right-hand side, you see those 4 little dots arranged in a square. That's where I will get a clue as to how correct my guess is. So I'm going to try red, red, blue, blue is my first guess. You got to start someplace. And depending on what the dots over there tell me, I'm going to learn something. So let's hit the question mark. Ooh, and I've learned that one of those colors is correct, but it's in the wrong position, which is what the white dot means. So I've learned a few things here. One of those colors is correct, and it's in the wrong spot. So I've learned that red is not in the first 2 positions, that blue is not in the last 2 positions, that there is only one of the color, and the color is either blue or red. Let's set all that aside for a minute, because we've learned something, but it's hard to put that in any kind of context yet. Let's do green, green, yellow, yellow. I've learned that one of those is in the right spot. That's what the black dot means, is that one of those is in the right spot. So I've learned that there's only one of a green or a yellow. And it's in the right spot. So let's make the last possible guess here. Orange, orange, purple, purple. And I've learned that there are, that 2 of those guesses are correct and in the right spot. So let's try to formulate some guesses that satisfy everything we've learned so far. The first one I see, let's assume that the orange and the orange are in the right spot. We don't know anything other than that yet. Let's assume that our yellow is in the right spot. And from the top row, let's assume that red was the right answer. So our first row tells us we had a red, but it wasn't in the first 2 dots. Well, that rule seems to satisfy that. Our second row tells us that one of the green or yellow is correct, and that seems to fit here. And the last one tells us that we had 2 pegs in the right position, but it doesn't tell us anything about which ones. So let's see what this tells us. Wow. And every single guess we made told us, well, at first glance, this would seem to have told us nothing. But it actually told us quite a bit. Compared to the first clue, we've learned that the answer is blue, and it's in either the first or the second position. Compared to the second clue, we've learned that, well, it's not yellow, so it has to be green. The only place we can put green that was in the right place is there. And based on our third clue, we've learned it's not orange, so it has to be purple. Now, there's still potentially some other possibilities here. I can see that green and blue might be reversed, but I'm pretty confident those are the right 4 colors. And that's the solution. I know Mastermind can seem a little confusing at first, but I regularly use it in my classrooms with students of all ages to teach concepts of computational thinking with data collection and analysis. It's a perfect example in a microcosm where you have to collect a bunch of data, and at each step you have new data that you can analyze towards finding a path to the solution. And if you have a copy of Donald Knuth's Selected Papers on Fun and Games, you can see I'm not just the only nerd that's come up with this as a cool topic, that Chapter 25 is a whole paper on the computer playing Mastermind. And before we go into the paper a little bit, I want to point out that he talks about the symbols being 1, 2, 3, 4, 5, and 6 instead of being colors in the game. That's an example of semantic erasure that we talked about during the abstraction video. And there's a whole algorithm here, actually the data based on what's called the Minimax algorithm, which we can get into with high school students, that talks about how you can progress through the algorithm of analyzing all the possible choices and how that you can get to any possible answer for this game within 6 moves. And you can see here, following semantic erasure, the first guess that he's based on here is 1, 1, 2, 2, which is exactly what I did with red, red, blue, blue. Battleship and Mastermind are 2 great games that illustrate the concepts of data collection and analysis, one of the tenets of computational thinking, but they are by no means the only ones. 2 other games that I often use in my curriculum are logic grid puzzles, which are puzzles where you get a partial collection of facts and you have to determine all the other facts that they imply. The other is logic dots, which is the closest thing I found that feels like debugging a computer program when you don't know how to program. So I may be talking about those in future videos. Thanks for watching, and stay tuned for videos on the other tenets of computational thinking.
G2.
Hit. I hate you.
Don't see that well on camera.
I don't care.